You execute a flawless calculation. You've substituted the values perfectly, cranked out the complex math right there in your head, and you're feeling great. But you still score a flat zero. Why? Because you made the agonizing, totally avoidable mistake of dropping your units or rounding just a bit too early.
Seriously, it happens every single year. You see, the examiner doesn't actually care how impressive your math skills are if your physics communication is broken. Today, we're completely bypassing the generic study tips. We're upgrading your last-minute revision into an actual, predictable scoring system for the Cambridge Physics 0625 alternative to practical paper.
Section 1. The Anti-Revision Strategy, Thinking Like an Examiner.
This right here is exactly why ordinary cramming completely fails for this paper. You're memorizing textbook definitions when you really need to be anticipating real-world laboratory disasters. Stop writing down vague, generic safety rules like wear goggles. Unless the experiment specifically involves lasers or splashing chemicals, that's not going to get you the mark. Instead, you need an examiner-approved risk assessment. Something super specific, like tying back long hair to prevent it from catching fire in a Bunsen burner flame. The examiner is actively looking for exact situational awareness. Think about the specific apparatus in front of you. Doing an electricity experiment, you've got to state that you'll prevent electric shocks by physically turning off the power before taking your measurements. Using a mercury thermometer, you have to acknowledge that dropping it creates a toxic hazard. Even stating you need closed-toed shoes is a valid point if you explain it specifically to protect your feet from falling heavy weights. It's all about pairing the specific action with the exact hazard. Take a look at this. This is the precise level of detail the mark scheme demands when they ask you about circuit safety. It doesn't just say, hey, be careful with the wires. It actively identifies the risks, burns, shocks, blowing out sensitive meters, and gives the exact operational solution. Switch the power off between readings. That is the gold standard right there. Section 2. The Highmark Answer Framework. In just a moment, I'm going to show you the ultimate examiner clue that changes your evaluation answers completely. But first, you need the foundational framework that makes that exact clue completely obvious. To spot those examiner traps and lock in your method marks on every single practical investigation, you need this 4-step framework. Step 1. Identify the core concept. What are we actually testing? Step 2. Pull in specific evidence or data from the experiment. Step 3. Apply your scientific reasoning. Why is this happening? And step 4, wrap it in the examiner wording. That's the specific terminology they are hunting for in the mark scheme. If you structure your descriptive answers like this, you are literally handing the examiner exactly what they need to award you full marks. Let's see this in action. Look how this framework takes a weak, typical student answer and upgrades it to top band perfection. Just writing used a timer only hits step 1. It's weak. But writing used a stopwatch, because automatic timers lack accuracy for this range, completely levels it up. It proves to the examiner that you understand the physical limitations of your equipment. Rule of thumb. In physics, anytime you substitute equipment, you absolutely must evaluate the accuracy of your alternative.
Section 3. Spot the examiner's trap.
Now we're getting into where the grade boundaries are really decided. I want you to pause and predict right now. Think back to your last mock exam. What is the absolute most common, devastating mistake students make when they have to evaluate measurements and draw graphs? If you guessed missing units, drawing a tiny graph that doesn't fill the available space, or swapping your independent and dependent variables, you nailed it. You've successfully spotted the examiner's absolute favorite traps. Rounding too early? That cascades into a massive error by your final calculation. And writing a conclusion that sounds great in theory but actually directly contradicts the data sitting right there in your table, that will instantly vaporize your evaluation marks.
Let's try a quick interactive challenge. Take a really close look at these 3 trials for a time measurement. Try to spot the 2 massive errors here that would instantly drop your grade. Focus on the header first, and then look at the spread of the data.
Got it? First off, the header is completely missing its unit. It just says time instead of time/s for seconds. Remember, never write your units next to the numbers inside the rows. They belong exclusively up top in the header. Second, that 9.5 is a blatant anomaly. It is totally wild compared to the 2.1 and 2.2. If you include that 9.5 in your average, you completely destroy the reliability of your mean. You have to actively state that you are ignoring the anomaly. So when you're writing out your evaluation, you want to use an authoritative phrase like this. It proves you're critically auditing the method, not just casually summarizing what happened. Please don't just write, the experiment was bad. State, the conclusion is not supported by the data because. and then directly point out that anomaly or the lack of repeated trials. You need to sound exactly like a lead scientist reviewing a lab report.
Section 4. Perfecting your final answer.
Before you even think about handing in that paper, you've got to lock down your terminology. Never just tell the examiner to do it again or try more times. That's conversational English, not physics. You must specifically state that you are repeating the measurements to calculate a mean. That is the ultimate bulletproof improvement for almost any setup because it mathematically smooths out random errors. It instantly signals that you actually understand reliability.
Treat this checklist as your absolute survival guide for planning investigations. Before you turn the page, ask yourself, are my units present in every single header and final answer? Do my significant figures match the precision of the raw data? Is my graph scale stretched out to take up at least half the grid? Did I address a specific safety hazard? Check off these boxes, and you make yourself practically immune to losing those silly, easily avoidable marks.
Okay, so you now have the exact framework to sidestep the most painful mistakes in standard investigations. But we still have a massive, unresolved problem. How do you apply this to the absolute hardest, multi-step graph analysis questions? You know, the ones Cambridge intentionally drops at the end of the paper to filter out the top-tier students.
If you aren't perfectly comfortable extracting gradients and cross-referencing them with complex formulas while the clock is ticking down, then this framework is only getting you halfway there. Leaving now means missing the exact walkthrough for this next hardest skill, which is absolutely mandatory if you want full marks. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click the video on your screen right now to seamlessly connect this exact framework into the full revision map for mastering advanced data analysis. Are you ready to conquer the most brutal traps the examiners have engineered? Jump into the next explainer right now, and let's lock in that perfect score.